Good morning. Today we will discuss noise in communication systems. Noise in communication systems. What is a noise? It is an unwanted electrical disturbance. Noise is simply, we can say, unwanted electrical disturbance which gives rise to the audible or visual disturbances. The noise, it gives rise to audible or visual disturbances in the communication systems and errors in the digital communication. Thermal noise. The noise which is generated by the resistors are nothing but thermal noise. The noise generated by resistors are called thermal noise. Thermal noise, it is random and which is continuous, which occurs at all the frequencies of matter. Also, it is predictable, additive, and present in all devices. Free electrons within a conductor, that means if we consider a conductor, the free electrons within a conductor are always random in motion due to the thermal energy received due to these free electrons. The distribution of these free electrons within a conductor at a given instant of time, it is not the uniform. The excess number of electrons may appear at one end of the conductor or other end of the conductor. The average voltage which is resulting from the non-uniform distribution is zero, but the average power is not zero. At this power, it results from the thermal energy is called thermal noise power. At this power, results from the thermal energy is called thermal noise power. Average thermal noise power is represented P suffix n equals to kTb watts. So here P is the power and n is the thermal noise. Pn equals to kTb watts, which is equation number 1. So here K is the Boltzmann constant, B is bandwidth of the noise spectrum, T is the temperature of conductor. This equation number 1, which indicates the thermal noise power, which is proportional to noise bandwidth and temperature, and it has a uniform spectral density. Equivalent circuits for thermal noise. Equivalent circuits for thermal noise. As conductor is generating an electrical noise energy, it must have an equivalent voltage or current generator circuit, which will represent the noise source. Let us see. So here this is a voltage generator for the noise source, and this is voltage generator equivalent circuit. This is the current generates equivalent circuit. And here if you see ES, it is the RMS source voltage. ES is RMS source voltage, but let us assume RS is the RMS source voltage, and here RL, it is the load resistance. RL is load resistance. This is the current I. Actually ES is the RMS source voltage, but we are assuming RS is the RMS source voltage, and here maximum power delivered to the load resistance RL, which is given as. So here voltage generator equivalent. Already we have assumed RS is the RMS source voltage. So maximum power is delivered to the load resistance RL. When RL equals to RS, we will obtain PL maximum equals to ES square by 4RS, which is equation number 1. So here ES, it is RMS source voltage. So here PL, it is load power maximum, and the same for conductor is given as Pn equals to En square by 4R. R is resistance here. From equation number 1 and 2, we will obtain Pn equals to kTb, or kTb equals to En square by 4R, or En equals to square root of cross multiplication root of 4 kT into Br. So this is the RMS value of the thermal noise voltage. Current generator equivalent. So the same logic for voltage equivalent circuit, which is applied. The RMS noise current is given as In equals to root of 4G kP into T. So where here G is the conductance, which is equals to 1 by R. Noise calculations. So resistors in series. So let the resistors act as the source of thermal noise. Let us the resistors act as the source of thermal noise. So let us connect the two noise sources, that is two resistors in series with each other. So here we are connecting two resistors in series with each other, so that we will obtain the resultant resistance is R equals to R1 plus R2. So noise voltage generated by the resistor R is given by En square equals to 4 kT into Br. En square equals to 4 kTb into R. So here En is the RMS noise voltage. En, it is the RMS noise voltage, which is in volts. So En square equals to 4 kTb into R. So 4kTb into here R already we have connected in series. So R1 plus R2. We are replacing R with R1 plus R2. 4kTb R1 plus we are multiplying this with this one. So 4kTb R1 plus 4kTb R2. So En square equals to En1 square plus En2 square, or En equals to root of En1 square plus En2 square. So if a number of resistors are connected in series, the resultant noise voltage can be given as En equals to root of En1 square plus En2 square plus so on. So here this is the value of En1 square, because here we are considering R1. Actually we have En square equals to 4 kTb R, but here 4 kTb R1. So we are replacing with En1 square, and here we are replacing in place of here R we have R2, so En2 R square. So this is En equals to En1 square plus En2 square. So here the resultant noise voltage can be given as En equals to root of En1 square plus En2 square plus so on. So effective resistance R is R1 plus R2 plus R3 and so on. Resistors in parallel. Already we have seen resistors in series. So resistors in parallel. So when the two resistors are connected in parallel, as the two conductors G1 and G2 in parallel. So here the effective value of conductance Gp equals to G1 plus G2. So here we have arranged these in parallel. So here In1 square. Here this is conductors G1. This is conductor G2, and here this is In2 square. So here the noise current generated by the conductance Gp is given by In square equals to 4 Gp kTb, which is equals to 4 into taking G1 plus G2 into kTb. So 4 G1 kTb plus 4 G2 kTb. We are splitting these two terms by multiplying with 4 kTb. So here noise current In square equals to In1 square plus In2 square. Short noise. Short noise, it is a form of noise that arises because of the discrete nature of the charges carried by the charge carriers, electrons or holes. Short noise, it is a form of noise which arises because of the discrete nature of charges carried by the charge carriers, electrons or holes. So due to short effect, short noise is produced in all the amplifying devices rather than in all the active devices. Short noise is produced because of random variations in the arrival of electrons or holes at output electrode of the amplifying device. Hence, it appears as a randomly varying noise current superimposed on output. So, short noise has a uniform spectral density like the thermal noise. The exact formula for this short noise can be obtained only for the diodes. For all other devices, an approximate equation is stated. The mean square short noise current for a diode is given by In square equals to 2 into I plus 2 I naught QB into AMP square. So here I is the direct current across the junction. I naught, it is reverse saturation current in amperes. Q is the electronic charge, which is 1.6 into 10 power minus 19 coulombs. So B equals to effective noise bandwidth in H. For the amplifying devices, short noise is inversely proportional to transconductance of the device, directly proportional to output current. So short noise is also called transistor noise. Partition noise. Next topic, partition noise. In the name itself we have, the partition noise is defined as a noise that generates when a circuit divides into two or more parts. Partition. In the name itself we have. So here when a circuit divides into two or more parts, this partition noise will generate. So partition noise, it is generated due to the random fluctuations in the division. The partition noise in the transistor will be higher than in a diode. The devices like gallium arsenide FET draw almost zero gate bias current, and therefore keeping the partition noise to its minimum value. So spectrum for the partition noise is flat. Next topic, signal to the noise ratio. Signal to noise ratio, it is a measure used in the science and engineering which compares the level of the desired signal to the background noise. Here it compares the level of desired signal to the background noise. So in the communication system, comparison of signal power with the noise power at the same point is important to ensure that the noise at that point is not excessively large. Signal to noise ratio, it is defined as ratio of the signal power to the noise power at the same point. So S by N, signal to noise ratio, which is represented as S by N, which is the ratio of power to the signal power to the noise power at the same point. So here PS by PN. So PS, it is the signal power, PN, it is the noise power at the same point. It is expressed in decibels, and the typical values of S by N ratio range from about 10 decibels to the 90 decibels. Higher the value of S by N ratio, better the system performance in the presence of noise. So signal to noise ratio S by N in decibels, which is equals to 10 log M PS by PN. So power can be expressed in terms of signal and noise voltages. So PS equals to Vs square by R and Pn equals to Vn square by R. Where Vs is the signal voltage, Vn it is the noise voltage. So S by N equals to Ps by Pn, which is equals to Vs square by R by Vn square by R. So here R get cancelled, we will obtain Vs by Vn whole square. So signal to noise ratio in decibels, which is given as 10 log base 10 into Vs by Vn whole square. So S by N decibel at decibels equals to, so here if you see this one, we will obtain from this 20 log base 10 Vs by Vn. So all the possible efforts are made to keep these S by N ratio as high as possible under all the operating conditions. Although the S by N ratio is often difficult to measure at the time, another ratio called S plus N by N, which is measured. Noise factor. The noise factor, capital F, of any amplifier or any network is defined as ratio of available signal to noise ratio at input to the signal to noise ratio at output. So noise factor, which is represented with capital F, signal to noise ratio, power ratio at input to the S by N power ratio at output. So here by giving these, we can obtain F equals to Psi by Pni into Pn0 by Ps0. So here I and O represents the input and output. So power ratio at output to the S by N power ratio at the power ratio at the input to the power ratio at output. So here we will write like this. So here Psi and Pni are the signal and noise ratio at input, and Ps0 and Pno signal to noise power at the output. So temperature to calculate the noise power is assumed to be room temperature. So the S by N at the input will always be greater than at output. Input is always greater than at output. So due to the noise added by the amplifier. Hence the noise factor is the means to measure the amount of noise added and will always be greater than 1. So ideal value of the noise factor is unity. Noise factor F is sometimes frequency dependent. F is sometimes it is frequency dependent. So ideal value of F is unity. And here F is the measure the amount of noise which is added and always be greater than 1. Then its value determined at one frequency is known as the spot noise factor, and frequency must be stated along with the spot noise factor. Noise output power in terms of F. Noise output power in terms of F. So power gain, which is G equals to Ps0 by Psi, or F equals to Pn0 by G Pni. So here we know that Pn0 equals to F into G into Pni. So Pni from this, we have Pni equals to KTB. So by substituting KdP here in Pni, we'll obtain Pn0 equals to Fg into KTB. But noise factor is determined at room temperature, which is given as Pn0 equals to Fg T0 into Kb. Fg T0 into Kb. With increase in noise factor F, noise power at output will increase. P0 P N naught is proportional to F. So higher the noise factor value, more will be noise contributed by the amplifier. Amplifier input noise in terms of F. Amplifier input noise in terms of F. The total noise referred to the input of the amplifier, which is given by Pni total equals to Pn0 by G. So here G is the power gain at the amplifier. Pn0 it is noise power at the output of amplifier. But F equals to Psi by Pni into Pn0 by Ps0. We know since G equals to Ps0 by Psi. So here Pn0 by, here G is Ps0 by Psi. So here we will obtain Pn0 by G into Pni. So Pni equals to P0 by F into G. By taking the cross multiplication, we will obtain this one. So we have Pn0 equals to Fg into Pni, but Pni equals to KTB or KT0B. So this is because noise factor is calculated at room temperature T0. So Pn0 equals to F into G K T0B. So in the place of Pni, we are replacing with this one. So Pn0 equals to Fgk into T0 into B. So Pn0 by G cross multiplication, we will obtain Fk into T0B, equation number 2. So from equation number 1 and 2, we will obtain Pni total equals to Fk T0 into B. So this is required from equation number 1 and 2. Out of this total input noise power, input source contribution is only KT0B and remaining by the amplifier. So Pni total equals to Pni plus Pna. So here Pna is the noise contributed by the amplifier. Noise contributed by the amplifier. So Pna equals to Pni of T minus Pni. So Pni of T, which is Fk T0Bn minus Pni is K T0Bn. So Pna equals to, by taking F minus 1 here, F minus 1 into K T0 Bn. So by taking common K T0 Bn, we will obtain Pna equals to F minus 1 into K T0 Bn. So this is the expression for noise contribution by an amplifier. So for an ideal amplifier, F is equals to 1 and Pna equals to 0. Noise factors of amplifiers in the cascade Friis formula. So let us consider two amplifiers which are connected in cascade manner. Since amplifiers are not used in the isolated manner, we connect as cascade. So here we have to observe the effect of the cascading on the noise factor and noise temperature. So here we have this diagram. So here arranged in the cascade. So amplifier 1, this is amplifier 2. So gain G1, gain G2, noise, factor F1, factor F2. And here Rs, it is the source voltage, and this is Pni equals to this one, K T0B, voltage source voltage. So here F1 K T0B, and here we have this amplifier 1, F1 G1 K T0B plus F2 minus 1 into M0B. And here we have Pn0 equals to G1 G2 F1 K T0B plus G2 into F2 minus 1 into K T0B. So this is amplifier 1. Amplifier 2, we have arranged in cascade. So let the power gain of two amplifiers be G1 and G2. So noise factors be F1 and F2 respectively. Total noise power at input of first amplifier is given as Pni total equals to F1K T0B. Total noise power at output of the amplifier will be addition of two terms, which is the noise input to the amplifier Pni2 equals to F1 G1 K T0B plus F2 minus 1 into K T0B. First term represents the noise power by G1. Second term represents the noise contributed by the second amplifier. So noise power of the at the output of the second amplifier is G2 times the input noise power to the amplifier 2, or we can write Pn0 equals to G2 into noise input to the amplifier 2. So G1 noise input to amplifier 2, which is G1 into F1 K T0B plus F2 minus 1 G2 K T0B. And here we have G2, we are multiplying with G2 here and here. Total gain of the cascade connection, which is given by G equals to G1 G2, or F equals to P N naught by G P N I, which is equals to P R naught by G is we are replacing with G1 and G2, G1, G2, P N I. We know the noise power supplied by the input source P N I equals to K T naught B, or F equals to G1, G2, F1, K T naught B plus F2 minus 1, G2, K T naught B by G1, G2, K T naught into B. So F equals to F1 plus, so by cancel these G1, G2, K T naught B here in this term, and in this term we will obtain, here we have only F1 and here we will have F2 minus 1 by G1. So by solving we will obtain F equals to F1 plus F2 minus 1 by G1. So same logic is extended to more number of amplifiers connected in cascade. Then the expression for overall noise factor F is given as F equals to F1 plus F2 minus 1 by G1 plus F3 minus 1 by G1 G2 plus F4 minus 1 by G1 G2 G3 and so on. The formula is known as Friis formula. This formula is nothing but Friis formula. F is congruent to F1. Remaining terms are small. Noise temperature. We know the available noise power equation Pn equals to K T naught Pn. Here subscript A, here this A indicates noise temperature, which is associated only with the available noise power. In general, TA is, will not be same as the physical temperature of noise source. For amplifier, it relates to the equivalent noise of the amplifier referred to the input. Let it be Pn naught. The equivalent noise temperature of the amplifier referred to the input is TE equals to PNA by KBN. We know that equivalent input power for the amplifier is given in terms of its noise factor by PNA equals to F minus 1 into KT naught into BN. So substitute equation number 2 in equation number 1. In this equation number 1, we will obtain TE equals to F minus 1 into T naught. It is found that noise temperature is better found for low noise devices, while noise factor is a better measurement for main receiving system. So let TE be the overall noise of cascaded systems referred to the input, and by TE1, TE2 so on are the noise temperature of individual stages. Then this formula is easily rearranged that, which gives the TE equals to TE1 plus TE2 by G1 plus TE3 by G1 G2 plus so on. Noise in FM systems, noise in frequency modulation systems. So noise in an FM receiver can be referred to input as shown in the figure. So noise at the receiver input cannot directly frequency modulate the incoming carrier. So here the noise phase modulates the carrier at the receiver, which leads to a reduction in input compared to the amplitude modulation situation. So in the case of frequency modulation, improvement in the signal to the noise ratio is achieved by increasing frequency division. So signal to noise ratio for frequency modulation is given as S by N REF is equals to RF by PN REF, which is equals to EC square maximum by 8 RSK TS into W. So here this is the frequency modulator receiver. Here this is E of t, which is N of t, and we are sending these two by here RF amplification here, and from here to mixer to IF amplification, and from here to limiter, detector, then IPF, low pass filter, LPF, low pass filter. So finally we'll obtain S by N here. This is the block diagram for the FM receiver. So let us consider the signal output from the band pass filter in the absence of the noise. So instantaneous frequency F1 equals to FIF plus delta F CD cos omega m into T. So frequency modulation detectors converts the signal output as Vm of t equals to C delta cos omega m into T. So RMS voltage output is EM equals to C delta F by root 2. Hence available power output, which is PSO equals to 3 delta f whole square by 8 R output here. So here the noise voltage output from the bandpass system, which is written as NIF of t, which is equals to N1 of t cos omega IF t minus NQ of t sin omega IF of t. So here signal to the noise at the detector. This is the diagram. This is the output here. This is the source voltage. This is the detector. The incoming carrier in this case is frequency modulated is E of t equals to EC maximum caused by omega IF t plus phi m of t. Here the incoming carrier in this case is frequency modulated is given as E of t equals to EC maximum cos omega IF t plus phi m of t, which is equation number 5. So here phi m of t, which is equivalent phase modulation produced by the signal. So noise analysis can be made assuming that unmodulated carrier is received. So input to the detector is E detect of t equals to EC of t plus NIF of t. So EC maximum plus N1 of t cos omega IF t minus NQ of t sin omega IF t, which is equation number 6. So a trigonometric analysis which gives psi of t equals to tan inverse NQ of t by EC maximum plus N1 of t, which is equation number 7. So when the carrier amplitude is greater than the noise voltage, phase angle becomes psi of t is congruent to tan inverse NQT by EC maximum, which is congruent to NQ of t by EC maximum, which is equation number 8. So frequency modulation is FIEQ of t equals to FIF plus 1 by 2 pi into d psi of t by dt. FIF plus, so here d by dt psi of t. So frequency modulation, which is given as FIEQ of t equals to FIF plus 1 by 2 pi into d by dt of psi of t. So here derivative of this. So here d by dt of psi of t, which is the value NQ of t by EC into maximum. So here we are replacing d by dt with dot here. So which is equals to FIF plus 1 by 2 pi. Here this is mistaken, 2 pi into N dot N Q, here this one. So d by dt means here we are using N dot Q of t by EC maximum. This is equation number 9. So hence noise voltage output is given as out O N of t equals to C here NQ dot of t by 2 pi EC into maximum. So this is the noise voltage output V suffix N of t, which is given as this one. So a result of Fourier analysis ST, if a voltage waveform V of t has a power spectral density G of f, we have GV of f equals to C square f square 2 kTs by EC square into EC square maximum. This is equation number 11. So from definition of power spectral density, noise power output is given as PNO equals to integration 0 to omega G nu GV of t df, which is equals to omega cube k square 2k ts by 3 EC square maximum. Equation number 12. The output signal to noise ratio is S by N output equals to P S naught by P N naught, which is equals to, we substitute 3 delta F square EC square maximum by 16 R output KTS omega cube. So the signal to noise figure for the frequency modulation is given as RFM equals to S by N output by S by N REF here. So which if you see the value 1.5 into delta F by omega whole square RS by R output. So here 1.5 beta omega square RS by R output. So this is equation number 14. Here beta omega, it is the modulation index. Beta omega, it is the modulation index. Noise in pulse modulation systems. So intersymbol interference. When a waveform is transmitted over a communications channel, frequency response of the channel introduce linear distortion, which is in the form of ringing. So the tail is result of natural buildup and decay energy in the inductive and capacitive elements in the transmission path. So with polar binary waveform, many of the tails can combine at some time to produce polarity inversion. So if the inversion coincides with the time, the bit error will occur while determining presence of 0 or 1. So the interference caused by tails is referred as intersymbol interference. Interference caused by the tails is called intersymbol interference, which we can call as ISI, intersymbol interference, ISI. So here, to avoid ISI with the rectangular pulses, the product of -3 decibels bandwidth and the pulse time width should not less than 0.5. So to prevent or minimize the intersymbol interference ISI, and this achieved through the pulse shaping. So here, next one definition, in the telecommunication intersymbol interference, it is a form of distortion of a signal in which one symbol interferes with the subsequent symbols. Let us see the eye diagrams. So eye diagram provides a useful way of examining a digital signal for the effects of the noise, ISI, and the timing filter. An eye diagram summarizes the effect of the ISI by showing the responses of zeros and ones here. So eye diagram can be generated by overlaying plots of the received signal for every symbol time. So resultant plot is look like eye. So it is called as eye diagram. It consists of the oscilloscope display in which the time base is synchronized to the bit rate. So let us consider the ideal signal as follows. So this is here NRH polar, non-return to 0 polar. So here non-return to 0 polar. Here we have 1. This is again 0, 1, 0, 1, 0. And here this is the time. Here TB, 2 TB, 3 TB, 4 TB, 5 TB, and so on. So this is the non-return to 0 polar. This is here a bit period is TB. So distorted signal. This is the distorted signal. Distortions we can see. So this is the diagram which looks like eye. So that's why this is called as eye diagram. So here vertical line here, and here this is bit period. TB represents here bit period from here to here 1, and here this is axis 0. Amplitude, this is amplitude. Here vertical line indicates that at this time eye opening is maximum as we go either direction. So eye opening is decreasing, which means ISI is maximum. If ISI is maximum, eye opening is decreasing. So this instant of time, we can take the decision making of a bit. So eye opening shows the ISI, that is higher the opening of the eye shows the lower the ISI, and lower the opening of eye shows the higher the ISI. So this is the eye diagram display. So this is the amount of distortion ones. So this is the distortion of zeros, and this is distortion of 1. So this is the margin over noise. And here this is the decision. This is the line distortion of timing. So here this is the distortion of timing. This is the distortion of timing. 0 volts here it is. So this is the best sampling inside eye opening. So this is the slope, you can see. So this is the margin over noise, This is the eye diagram. So there are many measurements that can be obtained from the diagram. So eye amplitude, eye crossing percentage, quality factor, eye delay. Thank you.